7 8 9 10 วิยังไม่เริ่มอัดฮัลโหล All right, so the recording finally started. Everyone see my screen, right? Yes, no?
Yes.
All right, perfect. Okay, so thank you so much. And by the way, thank you so much for everyone for watching the Eric Lander's speech on the Miracle Machine, right? So that's something I really find close to home in terms of like getting a good motivation, right? And also it gives you a groundwork of how you should build a community of researcher and how you should treat things like public funding versus privately like company funding, right, for research. But we should switch gear to the content of this class, right? So we will now talk about the two concepts that built your CPU. One of the primary concepts that goes into your CPU and the GPU to basically most of the processor, if not all, will use things like pipelining, right, to make it fast. But before we go there, let's go reviewing what we went through in lecture 2 a little bit, right? We talk about the ISA, the instruction set architecture, and we talk about the microarchitecture, which seems like a two words that has the same thing, the word architecture in them, but they are different in the sense that the ISA will define the list of commands that the microarchitecture can understand. So that's basically treat ISA as a book of rule where the programmer can issue these commands, right? If I want to write a program on a chip, I can issue all these commands, which also means that the hardware, the microarchitecture, which is the hardware, has to implement the command in the circuit. This is a physical thing and has to implement the command, right? So the microprocessor that we use are ISA plus microarchitecture, right? It's the interface between the software and the circuit. And we talks about what goes into the ISA, things like instruction, the opcode, addressing mode, data types, instruction format, the register, condition code, memory, address space, alignment. So these are the things that you might have learned from undergrad years. And if you haven't go through like a CS undergrad or computer engineering undergrad, that's okay too, right? Just imagine when you want to order your computer to do something, you need the subject and you need the verb in the sentence, right? Go add this number and this number. The verb is add. The subject and the object is the two numbers you want to add and the resulting number that you want to produce the result for, right? So that's opcode and operand, right? And when you have to go access your memory, there has to be a way for the programmer to access DRAM, right? So the ISA will specify that. ISA would have to specify things like how do I call or interrupt. Let's say I like hit the power off button on my computer, right? It sends a signal saying, I want to kill everything that's running right now, right? So how does the ISA handle that? It will specify how the hardware should handle someone hitting the power button, right? Or the reset button. And it would actually have to manage things like access control, right? Who get to access what? What's the priority, right? If I want to print something to my printer versus I want to run a game on my laptop, which one has more priority, right? What's the threat management policy? What's the power and thermal management policy? These are all encapsulated in the ISA. And ISA are what is visible to the programmer. So as a programmer, you can write assembly code that send the command. These are what is available and basically observable from the programmer, right? And then there's also things that are invisible. Things that are invisible from the programmer, where these are in the microarchitecture level, right? Oh, sorry. This is called the microarchitecture. Sorry about moving the slides, right? These are the policy inside the hardware and how I implement my hardware, I don't tell the programmer how, because I don't want you to worry about that. I want this to work magically, like this magic black box. You issue the command, it magically appears as a result. I don't tell you how the process of that is done. In this class, we'll learn how that process works, right? So the microarchitecture basic, right? I say it's a method. Microarchitecture would move from state 1, architecture of state 1 that the programmer see, to the next state after I process one line of assembly. So this is basically one line of assembly, right? I run one line, something happened, magic happened. It actually involved multiple steps. But from the programmer point of view, you just say, hey, I moved to the next line, right? And this is nice, right? If you think about it, it's like, if you think about it, basically, if you run Python code, you run one line, something changed, and it changed correctly. It's perfect, right? So that's how the microarchitecture works. The goal is to make sure you process the instruction correctly, right? And we talk about this thing called Datapath and control logic. Datapath means that is the circuitry that allow you to process the data from D1 to D1 prime. Let's say you add the data get added, right? The data path would be the adder, would be the wiring that goes into the adder and things like that, right? This is done through, sometimes we call this functional unit, or sometimes we call this ALUs, as well as register, basically the components that goes into what is there to transform the data for me, right? Instruction would tell what the operation is, right? And the data part, again, transform D1 to D1 prime. The control logic is the one that signal when each component should trigger, and should trigger what? It select the correct things into the adder. It select the correct operand into the memory so that you can get the address that you want. These are all the control logics, right? The tasks of the control logic. And we kind of ended with our toy example, right? So what is the instruction register or the program counter? Can someone tell me what is the program counter?
It is a pointer that point to the memory address.
Yes, thank you so much. It's when they point to the memory address, it tells that is the line I'm running right now. This is like, if I freeze time, the program counter would tell this is the line that I'm running in assembly. Because assembly has multiple lines in your program, right? It points to the current line that you're running. So that's the program counter. And as you said, it points to the memory. So I can have the instruction register. By the way, it's the same thing. IRPC, same thing, right? Now I point to the memory. I give them an address, right? So now we're done with the program counter. I have an address. What do I get from that address? So let's say it points here. And it's just a bunch of 0 and 1s. It's just a bunch of 0 and 1s, right? But if you look at the ISA manual, that 0 and 1s would tell you it's an add, it's a multiply. So it basically that instruction in the flesh, right? Basically that instruction in the flesh. So you bring in that whole pattern, right? 0, 0, 1, 1, 0, 0, 1, or whatever comes in, that becomes an instruction. And by this point, let's say point A, right? Point A, does the computer know what the instruction is yet or not? Do I know what the instruction is this, or do I just know the bit pattern? I'm trying to crack what the instruction is.
No, only the bit pattern.
Only the bit pattern. Yes, thank you so much. You just got the bit pattern. Now you feed the bit pattern to what we call the decoder. This is one of the core elements of any processor. It converts the bit pattern And it allowed the computer to look into the bit pattern and figure out, okay, that's an add. I want to add this number with this number. So I'm gonna go and select. So let's say it's an add. Let's assume this is an add instruction. You would first select, what do I want to add from? You would take the thing you just select, right? And again, it would select the correct things that feed into the adder. If you need to get the data from the memory, it also would handle, right? Hey, I'm gonna get the data from memory. Here's the address, right? Now I have the instruction. I just kick off the adder, say, hey, add the two numbers together. What do I get as a result? Let's say this is like add A plus B and write it into C. So what goes into here, the adder as an input? What goes into the input?
A and B.
A and B, right? So basically the decoder would select A and B into the adder. It's actually as simple as that. Hey, I want A and B from my command. I'll just select A and B, feed that to the adder. I want the results back, right? So the data coming out here is data C, right? That comes out. And what do we do next? Now I have the results from the adder, but I haven't saved it yet. So what is the next thing do I have to do? I have to, yes, sorry.
อ๋อครับ
Go ahead, go
Store
ahead.
in register file again.
Yeah, exactly. Put the result back, right? Because that's an output and I need it for the future instruction. So I will put it back, right? Basically now the decoder again would select what do I put back to the register file. So I would pick the right thing. In this case, I have the input from source 1, source 2, and source 3, 3 different wiring, one coming from directly from the decoder, one directly from the ALU, right? The other one from the memory. Which one should I select? 1, 2, or 3? From this diagram, do I select number 1 or number 2 or number 3 into the register file?
Number 2.
Number 2, right? Because the number 2 is the result from my adder. That's the correct thing I need to do. So this select would say select number 2. Number 2, that's the data comes in, goes into here and goes into here, right? And you'll see what happened to the left side in a bit, because sometimes your instruction is not an add instruction. Let's say it's a jump instruction. I want to move from this PC to a different value. That can spawn, right, an input directly into the PC. But in this case, we are not doing that. So we just want what? We just want the next instruction, right, in my code. So I just want the next instruction in my code. How do I get that? Again, select PC plus 4. So this is input 1, input 2, input 3, and input 4. What should this select pick? 1, 2, 3, or 4?
Number 1.
Number 1, right? So it select 1. So that it picks PC plus 4, right? It picks PC plus 4. Feed that to program counter. So it goes to this line, which is whatever is in the next line. And that's it. We just did one instruction. So since we just did one instruction, can I do the same thing for your entire program? Can I keep doing this? Yes or no? You can do thumbs up too.
Yes.
Yeah. We keep doing this until the program finished and now you're done with the program. Simple? Yes. Complicated? Also, yes. So from the abstract view, from the really high level, you just look at our toy example, right? It's actually pretty simple. I process the instruction by first trying to figure out what that instruction is. Then you take the right component, feed that to the right functional units. Then you select the correct output and do the same thing over and over again until your program is done. Until your program is done. Every single processor, be it the CPU, the GPU, Even things like the TPU fundamentally work the same way. Every single processor you know on this earth works the same way. I guess maybe except quantum computing, but to make it easily programmable, it would have to work the same way too. Otherwise, you can't really program them easily. This is the fundamental reason why I can process my assembly code as long as I have all the hardware, right? So let's do a simple add again, right? But now we do step by step and we'll name each of the steps. The first step we call a fetch. What does fetch mean? What does fetch mean? So anyone here has dogs? มีใครมีน้องหมาที่บ้านไหมครับ
มีครับ
คนที่มีน้องนิวมีน้องหมาที่บ้านเคยเล่นแฟชไหมแบบพาลูกบอลมาให้น้องหมาเก็บ
อ๋อ ไม่เคยฮะ
โอเค ก็คือ so basically fetch if you compare that to like when you play fetch with a dog, right? You have, let's say you have a toy, you can throw it out, right? What your dog would do is they would go and grab the toy and give it back to you. So that's fetching. Computer kind of works the same way. You give them the address. You give the computer the address. The computer, the CPU, and will basically go to the memory, fetch the instruction, give it back to you. Right? So the fetch process is from PC right here. You go to the address, you get that instruction. The instruction comes back to the decoder. So this part is called fetch. Any question here? Any question here before we move on? That's what we define as fetch. All right, so the next step, right, is decode. Anyone want to take a guess where decode happens?
Recorder.
It's in the decoder. That's it. Basically, you have instruction coming in, right? And the decoder figure out what do I do? It figure out what do I do. So it will select whatever is correct thing for the register file. It select the correct thing for all this signal, right? So that's what the decode phase is. It's select it's heavily involved with control part, right? It heavily involved our control part or the control logic, because now you know what the instruction is. You send out the signal saying this component do this component do that to make sure I can execute the instruction. Then the intermediate step within the decode is to fetch the operand. Now it's basically select to the register file, or you send the constant value from your instruction directly to the adder, or you can go and fetch something from the memory as well as an input to your operation, right? So that's fetch operand. Then once you have all the inputs, now you have, right, all the inputs. You execute. The execute phase is this part. I run it. I run my command, right? Then the last step is I want to store the result. I want to store the result. Sometimes this is called write back. So you write the result back either to the register file or the program counter. Basically, that's when you commit, right? When you commit and finish up the command before you move to the next line in assembly. Anyone notice I forgot one component completely? So I kind of talk about everything in here, right? Which one did I forget to mention? So execute involves the ALU, decode involves the decoder, write back involves the register file, and program counter. Which one didn't really talk much?
Memory.
The memory, yes. So typically, if you have to deal with memory, it would be the stage between execute and write back, right? So what is the typical steps? You would first get the instruction, decode it, execute. If you have to go to the memory, you have memory state, and you have the write back, WB, write back. I typically would use the just one letter W, but because of my own handwriting, which is really horrible, I would use WB so that it looks different from memory. All right, I'm sorry about that. My handwriting is terrible. But now let's talk about what happens if I have a load. So let's say I want to load this. I want to load R1 plus 4 into R0. This basically means that, let's say R1 is 20, right? I add 4 to that. This whole thing become my address. And this is the same thing as, let's say in C code, you have say A equal, right? Pointer that points to address 24. I have address 24. I want to load that to my R0. This is my R0, right? So let's talk about that memory instruction. Again, right? You first fetch the instruction, which you get some random bit pattern, right? And that random bit pattern goes into your decoder. Decoder figure out, oh, okay, it's a load. It's a load. 0 and then R1, 4, right? I want to add R1 plus 4. So how do I get R1 plus 4? What should I select here? What should this select? I want R1, right? What is the address I want to fetch? R1 plus 4. So this select should select R1. It selects R1. What is the second operand to my load here? Again, remember it's load R0, R1 plus 4, and this thing is my address. So in order for me to get this address, I need to do what? I need to do add what and what together. I want this to be R1 plus 4. I want R1 in here, right? Okay. Here, I want R1 and I want what? 4. 4 can come from here or through the immediate. R1 can come from the register file. Then you enable the adder because then you want to add R1 and 4 together. The result is R1 plus 4. Instead of feeding that to the data, you actually feed it to the memory as an address. Then you get the data comes back here, right? You then enable that you want to write that data, which is whatever address R1 plus 4 into R0. All right, any questions? มีคำถามไหมครับ ครับ
คือ4นี่มาจาก immediate ใช่ไหมครับ
ใช่คือตัวเลข4จริงๆแล้วถ้า decoder มันเห็น instruction เรามันจะมีเลข4อยู่ในนั้นอยู่เป็นส่วนหนึ่งของ instruction อยู่แล้วคือไอ้โหลด R0 R1 บวก4เนี่ยมันเลข4มันจะเป็นพาร์ทหนึ่งของ instruction เราที่เป็น pattern 001ของเราเนี่ยมันจะมีแบบ0000100ที่พอแปลงเป็นฐาน10คือเลข4อยู่แล้วใน ISA มันจะบอกว่ามันเป็นบิตไหนใน instruction ของเรามันใน ISA จะเป็นคนบอกว่าเราจะ extract ไอ้เลข4เนี่ยออกมาได้ยังไงแล้ว decoder มันก็จะไปแค่แบบไป extract มันออกมาตามคำสั่งของ ISA แล้วมันก็จะเจอโอเคนี่คือเลข4โอเคนี่คือการที่เราต้องไปเอา R1 มันก็จะไปเอา R1 จาก register file แล้วมันก็จะเอาเลข4จากตัว instruction ของเราโยนเข้าไปที่ adder และ adder ก็จะบอกโอเคงั้น add จบแล้วก็ add แต่แทนที่ add ออกมาจะเป็น data ใช่ไหมคราวนี้มันเป็น address เพราะเราต้องการไปโหลดมันก็จะเอาไอ้ R1 plus 4 ส่งเข้าไปที่ memory เป็น address แล้ว memory ก็ค่อยให้ data กลับมาที่ register file เห็นภาพขึ้นไหมครับหรือว่ายังงงอยู่
เข้าใจแล้วครับ
โอเค น้องๆมีใครมีคำถามเพิ่มไหมครับถามได้นะ เพราะว่าอันนี้คือเป็น1 สไลด์ที่อาจจะงงได้
เอ่อผมเดี๋ยวผมขอพูดเองแล้วอาจารย์ดูว่าถูกไหมนะครับ
โอ้ได้เลยยินดี
โอเค ก็คือสมมติว่าเป็น R1 part 4เหมือนกันใช่ไหมครับ ก็มันจะทำเป็น address ก็คือเป็นมันก็จะได้เป็นเลขออกมา อันนี้ถูกต้องไหมครับ แล้วก็เข้าไปใน memory ก็จะเป็นเลข 010000 something something อันนั้นก็เอาเข้ามาใน decoder ซึ่ง decoder ก็จะมีมันก็จะได้ instruction มาก็คือจะเป็นมีโหลดมี R1 มี R0 มี 4 ซึ่ง R1 ก็จะอยู่ใน register file
ใช่
ใช่ไหมครับ แล้วก็ 4 ก็จะมาจากการ decode ออกมา
ใช่
แล้วก็เอา R1 กับ 4 เข้าไปใน ALU แล้วก็มี add เข้ามาด้วยจาก decoder
ถูกต้อง
จากนั้นพอโหลดก็จะไปเอา address ใน memory ใช่ไหมครับ แล้ว data ที่จาก ALU เข้าไป memory นี่คือ
อ๋อ อันนั้นคือเผื่อสมมุติถ้าเราเป็นถ้าไม่ใช่โหลดแต่เป็น store ก็คือเราต้องการเอาเก็บค่าใส่กลับไปที่ memory อ่ะ คือไอเส้น data เนี่ยผมวาดไว้เพราะว่าบางทีเราต้อง support store เหมือนกันนะไม่ใช่แค่โหลดอย่างเดียวเท่านั้นเอง
โอเคครับแล้วจากนั้น data จาก memory ก็จะเข้ามาตรง register อีกครั้งหนึ่งเพื่อเอามายัดใน R0
ถูกต้องครับ
แล้วก็จาก register ก็จะถูกส่งออกไปข้างนอก
ก็ PC บวก 4เฉยๆจบไปบรรทัดต่อไป
โอเคนะขอบคุณครับ
โจถูกต้องครับเรียบร้อย ก็ตามนั้นเลยครับ ก็คือ พอเราค่อยๆทำทีละสเต็ปจะเห็นภาพใช่ไหมแล้วถ้าน้องๆงงเรื่องมันมี signal ที่เข้าไปใน memory มี address มี data จริงๆแล้วมันไม่ได้คือถ้าเราดู high level เนาะให้เรามอง memory เป็นเดี๋ยวขอสไลด์ต่อไปมันเป็นที่ว่างเยอะผมว่าในนี้ก่อนให้มองว่า memory มันเป็นก้อนหนึ่งใช่เป็นก้อนหนึ่งแล้วเราสามารถใส่ address เข้าไปได้ เราสามารถใส่ data เข้าไปได้ แล้วก็ output ของมันสามารถ output data เข้าไปได้ มันจริงๆมันมี input อีกมันจะเป็น read หรือ write ก็คือถ้าเป็น load ก็จะเป็น read ใช่ไหมเราก็จะ read แล้วใส่ address ที่ถูกต้องเข้าไป memory ก็จะพ่น data ที่ถูกต้องออกมา นี่คือการ load ถ้าเราต้องการ write เราก็ใส่ address เราใส่ data แล้วเราใส่ write มันก็จะไม่ได้พ่น data อะไรออกมา มันจะพ่นแค่บอกว่าเสร็จแล้วนึกออกใช่ไหมครับมันก็ operation มี2 อย่างเขียนกับอ่าน ถ้าเขียนเราก็ให้ address บวก data ที่เราจะต้องการเขียนแล้วบอกว่าอันนี้คือการเขียนนะมันก็จะไปจัดการของมันอันนั้นแหละครับ Alright so can we move on to handling branch Alright so let's go back to our toy example what if we have a branch let's say we want to do this jump to R0 plus 4 what does this mean it means I want to jump to I want my next PC, the PC in the next cycle, to point to R0 plus 4, not PC plus 4, right? So that it basically goes into here, you fetch jump R0 plus 4, right? So the decoder select, right? It selects R0, it select 4 in here, go into the adder. You got R0 plus 4 coming out to the data, right? As the data, basically. Let me erase that line because I already have that data line. So this data coming out from the adder is R0 plus 4. Do I forward it back to the register file or do I do something with my R0 plus 4? What do I do here? I have the result. What do I do? This? Right. Oh, sorry. I know that you opened that. Yeah, go ahead. Sorry.
พอก็จะตอบอันนี้นะครับ
Oh, okay. All right. So basically, your next PC would take in this, right, input. So you have number 1, number 2, number 3, number 4 as 4 potential signal that can go into the next PC. So which one should it select? Select 1, select 2, select 3, or select input 4? Which input should it select? Input 2, right? Input 2 is where R0 plus 4 is coming out from. And that's your next PC. And that's all. That's how it handles branch in your code, which is how it handles if-else statement, right? So, so that's all for a single cycle instruction and a single cycle processor. Everything is done in one cycle, right? We have all the control signal that's generated, and you transform D1 to D1 prime. Basically, you finish one line in assembly in one single cycle, right? Multi-cycle processor means that I can stage them. I don't have to finish everything in one cycle. It allows you to decouple the control signal from the data path. But let me ask you this question. From here, from this scenario, right? Which one seems better? Which one seems better? So let me ask you this. My ISA has to support 4 operations. And let's say I have a really dummy ISA. I can do add, I can do subtract, I can do multiply, and I can do division, right? 4 instructions. And let's say the adding take 1 nanosecond, subtract is 1 nanosecond, multiply is 10 nanosecond, and division is 100 nanosecond. If I use single cycle processor, how can I clock this? Which operation here determine how fast is my clock? If I use single cycle processor, which operation here would dictate how fast is my clock?
Division.
Division. I have to wait for the slowest guy. I have to wait for the slowest instruction. If I use multi-cycle processor, what does it mean? Can I clock this at the 1 nanosecond rate? If I am adding, I finish that in 1 cycle. If I want to do a multiply, how many cycles do I have to wait until I finish? One cycle is 1 nanosecond. So if I have to do a multiply, how many cycles does it take? Let's say I have to do an add, I have to do a subtract, I have to do a multiply, and I have to do a division. So that's my program. This is my program. So in a single cycle processor, how long does it take for me to do an add? How many nanoseconds? What dictates my clock? Again, you have to go back here, right? And it would answer what determine my clock. So now 1 clock cycle is 100 nanoseconds. I finish an add in 1 clock cycle. So how long does it take for me to finish adding? I want to add 2 numbers together. How many nanoseconds does it take? I take 1 clock. New I thought you turn on the mic.
Oh, one clock.
Yes, 1 clock in a single cycle processor. A single cycle processor, my clock has to go with the slowest instruction, which is the division, right? So now in the single cycle processor, 1 clock one clock is 100 nanoseconds, regardless of what instruction I'm running. So I want to just add two numbers. I have to wait 100 nanoseconds. I want to subtract, I wait 100 nanoseconds. I want to multiply, okay, wait 100 nanoseconds. I want to divide, I wait the same 100 nanoseconds. Because that's the smallest unit, that's one clock, right? That's one clock. How about multi-cycle? I want to do an add. I can just spend one cycle for that. So it's 1 nanosecond. I want to subtract, again, sure, 1 nanosecond, 1 clock. I want to do the multiply. Multiply take 10 nanoseconds, so I'll just clock it 10 times. I'll just do the control my signal the slow way, right? So I just spend 10 nanoseconds. And division, I'll spend 100 nanoseconds. Which one's better? Single cycle or multi-cycle?
Multi-cycle.
Multi-cycle. Because for single cycle, even though everything finished in one cycle, I have to wait for the slowest instruction. So my clock will have to be clock based on the slowest instruction. For multi-cycle, I don't care. As long as I can clock the logic fast enough, which in most cases you can go with like 1 nanosecond or lower, right? A 3 gigahertz processor clock once every roughly 0.3 nanosecond, and we can build a logic for that, right? So in this case, multi-cycle is better. So we are going through that next. In the meantime, let's take a quick break. How about we do a 10 minutes break and we resume at 10:06 a.m. I'll get some water. I'll be right back, right? And I'll stop the recording so we have multiple parts for the lecture on YouTube video. I haven't shared you the link, right? I'll do that right after this class. We have a playlist for our YouTube video for lecture 1 and lecture 2, and will be for this lecture as well. So let me stop the recording for now.